All right. Welcome back to Codex. Our speaker today is Christopher Heil from the Georgia Institute of Technology. Professor Heil got his PhD from the University of Maryland under the direction of John Benedetto, and has been a leader in the field of applied harmonic analysis ever since. His work on wavelets and Gobber systems has not only been groundbreaking in its own right, but has also inspired and guided a great deal of work in those fields. In particular, his HRT conjecture must be mentioned for all the great work in harmonic analysis it has inspired. Professor Heil is also a noted expositor of mathematics. He has authored several books, is a co-author of the widely used Thomas's Calculus series, and even has additional not yet published expository texts posted on his website. We're very pleased to have him today to discuss frames, erasures, and excess in infinite dimensions. Take it away, Christopher.
Well, thanks very much for the kind introduction. So the Codex seminar that I've been attending for a while now, it seemed to me that most of the talks were aimed at people working in finite frames. And I was a little worried about this giving a talk because I don't work in finite frames, not having been smart enough to realize that finite frames are really interesting. And so I stayed in infinite dimensions. Uh, but last week, Hartmut Führer gave a very interesting talk. It was quite abstract. And what I'm going to do in this talk is try to give some of the background and examples of things related to things he talked about. And in some sense, I'm going to focus on the pathological things that go wrong in infinite dimensions. So I want to go all the way back to the original frame paper by Duffin and Schaeffer, 1952. It's a beautiful paper. If you've never looked at it, I do encourage you to take a look at it. It has most of the basic results about frames already in that paper. They proved, for example, that the frame operator is invertible. They defined the dual frame by applying the inverse frame operator to the frame elements. And they showed that the frame and the dual frame give you representations of elements, not necessarily uniquely, but you have these canonical representations given down at the bottom of the screen. They also showed, they characterized the other coefficients that you can use to represent a given vector, all the alternative scalars Cn that you can use. Those lie on a kind of hyperplane that's perpendicular to the canonical choice of scalars. And the second bullet there, it has an asterisk next to it because I don't think I saw that in the original paper, but it's an easy corollary of the other things that they did. And from it, you can see that if the inner product of a frame element with its corresponding dual frame element is 1, then those two elements are then you have an orthogonality condition between that frame element and the other dual frame elements. And because of that, it follows that a frame has a very interesting property. When you take out an element from a frame, there's only two things that can happen. Either you have completely destroyed it in the sense that it becomes incomplete, or it has enough redundancy that when you remove an element, you're still a frame. And of course, in finite frames, this idea is very important. This idea of losing elements, it becomes the topic of erasures, and we want to know how to reconstruct even when losing things. I'm not going to focus so much on that, just as the fact that we can remove things. And in fact, I'm going to look back at an earlier result, a very beautiful result itself by boisPollard from 1948 that's inspired by this issue of removing elements. And again, a very beautiful paper. They asked the question, what happens if you have an orthonormal basis, let's say for L2 of 0, 1, and you take out finitely many elements? You've certainly destroyed the completeness. Is there a way to somehow restore the properties by some simple operation? And the operation they had in mind was just, can I multiply the remaining functions by something to restore the completeness? And they proved that, yes, you can always do that. And for the case of taking out just one element, it's actually a very short and nice proof. You just choose an element so that, say we take out the 0th element. We choose a function so that f0 divided by m is not L2. So if you're thinking about something like the complex exponentials as your orthonormal basis, the 0th element is the constant function. So you're just looking for something whose reciprocal is not L2. Right? So you need a function that has a singularity. You don't want it to be 0 on any set of positive measure because you won't get the completeness that way. But it's not really hard to construct these functions. And the reason that you're still complete then is, suppose that you had a function that was orthogonal to all of these products, the fk times m's. All right, well, that's just an integral. Move the m across to the other side to be connected with f. It's just f times m conjugate inner product fk. So f times m conjugate is orthogonal to all the elements except one. And therefore, it's a multiple of that one. But the way we've chosen things, f0 divided by m is not L2. So the only way this can happen is if that constant multiple is 0. So f is actually orthogonal to every single f sub k, and therefore it's 0, and therefore my set is complete. So you can certainly do this without too much trouble when you delete just one element. And then you do an induction. It's a little harder than you might think, but it's not super hard, but it's an interesting induction, and you can extend to any finite set. So, you can always restore the completeness by this method. And just to say a little bit more about constructing this thing, it's not hard to do. You just want a function that whose reciprocal is not L2, and you have some arbitrary function f0, but someplace that is non-zero on some set of positive measure. It's bounded below on some set of positive measure, and so just multiply by your thing whose reciprocal is not L2 on that set, and outside you don't care. But there's something interesting about this construction. I mean, if you want to try to generalize this, you need to be able to construct things whose reciprocals are not L2. And so there is some restriction in there. You need some kind of non-atomicness in your measure in order to make this work. And here's a sample lemma that just shows that you can generalize the heck out of this thing. There's nothing special about orthonormal bases in this construction. There's nothing special about orthogonality, uniqueness, anything like that. The same proof applies to a frame, even to much weaker things. But what's essential is somehow that non-atomicness, that you can take very small sets and do something with them. And so you can see, for example, in little L2, this just doesn't work. Take the delta sequence. If you throw out one of the deltas, there's no way to multiply the remaining things by anything and get back to a complete set. It's just not going to work. So there are some limits to how far you can generalize this thing. And the amazing thing is, I came across that paper by boisPollard.
Hey, Chris.
Go ahead.
I'm sorry. On the previous slide, what is a solid Banach space?
That's a good question. So a solid space is one like L2, where suppose that you have two elements, f and g, say functions, and if g is in the space and the absolute value of f is less than the absolute value of g, then f is in the space. So you have kind of you're respecting absolute values. Once you have a function in the space, any smaller thing is still in the space. That's true in the LP spaces, just kind of trivially, but it's not true in a lot of other spaces. Like if you take the Wiener space, the space of functions, the Fourier transforms of the L1 functions. that doesn't respect an absolute value anymore. And functions that are defined by something other than just absolute value will not be solid. So when I was a grad student, this was back so far that many of you won't remember this, but in those days, I had to go to the library and search for hours on end for papers and just look them up and go from one journal volume to another and Xerox all the papers and look for things. And one day I came across this boisPollard paper and brought it to John along with another paper by somebody named Jim Burns that I had found. And I was really surprised because John knew both of these people, Pollard and Burns. And it was a real pleasure to surprise him with papers by people that he knew, but he didn't know the papers. But later, I found that this issue of restoring the completeness had been generalized, or had been extended by a number of people, well, in surprising ways. This result I'm talking about is part C down at the bottom, right? You've got a system. When can you restore the completeness by multiplication? There's some results here by Talion and by Price and Zink that give you equivalent representations of this. There has to be a set of large measure so that just multiplying by the characteristic function of S is complete. And not only that, you can do some kind of approximation by something in the span on a large set. And all those turn out to be equivalent. And also I should mention that there are quite a number of other related and somewhat surprising results by Kazarian that I'm not going to go into here. But this issue, I want to now give an example of a system where we actually do this multiplicative completion. But before doing that, let me remind you about some systems that we're pretty familiar with, which are the orthonormal basis of exponentials times a single function. I call these weighted exponentials. Via the Fourier transform, this is very closely related to sets of translates, which I'll talk about in a minute as well. But these kind of things where we take all the exponentials times a weight, we know exactly what happens for these systems. We know when they're complete, when they're minimal, which means that it has a biorthogonal sequence, or that there's no element that's in the closed span of the others. We know a lot of things here. The interesting things in this list, perhaps, are item C. We know when it's a Schauder basis, when you can use these to represent things uniquely, but not in the way that a frame does necessarily. There's a conditionality to it. You have to choose an ordering in a Schauder basis, whereas frames, the representations converge unconditionally. But there's an interesting characterization of the Schauder bases. It's a little bit stronger requirement than being minimal. Minimal just requires that you have a biorthogonal sequence. A Schauder basis requires that when you do the partial sums using that dual sequence, like you do in a frame, they actually have to converge. And if you look at the conditions for minimality, when will the weight give you a minimal system? You just need that the reciprocal is L2, right? Unlike the previous situation where we wanted something that wasn't L2. If 1 over g is L2, then 1 over g times the exponentials are orthogonal to the exponentials times g. That gives you your biorthogonal system. But you need something a little extra to get convergence. And that's the condition that's given in part C. you need your weight or your weight squared to be in a special class called the Muckenhaupt class. And it requires a little bit more than being just the reciprocal being square integrable. There's a kind of size requirement on different intervals within 0, 1. I'm not going to get into the specifics of that, but it's something a little bit stronger. And if you go much stronger than that, if you go to the point where you require that your weight be bounded above and below, that puts you down in the Reese basis situation. You're a frame and a basis at the same time, and you have unconditional representations. And most of these, aside from C and E, are easy to prove. And E is due to John and Shidong Li. And it characterizes when you are a frame not for the whole space L2 of 0, 1, but just a frame for your span. And in that case, you have to be bounded above and below, but only on the place where you're non-zero. So you can be 0 on sets of positive measure, but aside from that, you have to be bounded above and below. Aside from C and E, the others are really easy to characterize. But that's not quite the situation that I'm really interested in. I'm interested in deleting things. So if you take your exponentials and throw out something, you're no longer in this situation here. Right? This presumes that you have the whole structure, you have all of the frequencies indexed by the integers. So throw out something. Throw out, let's say, the 0th element, the constant sequence. And you get a neat example. So we can see directly what we need to multiply by to restore completeness. We need something whose reciprocal is not L2. Take 1 over x. That's not L2. So if you multiply by x, take x times e to the 2 pi I n x, that's complete. Now, you know it's not going to be a frame because x is not bounded above and below, right? The full thing with taking all of the indices. But it's still complete. And this one is interesting because you can actually compute and see that it has a biorthogonal sequence. If you take the inner product of xen with en minus 1 over x, when m and n are not 0, those turn out to be orthogonal. And so these two systems are biorthogonal to each other. And that means you've got a minimal system. So this system is actually better than just being complete. It's minimal. You can't remove a second element. You can only take out that one element, the 0th element, from this x times e to the 2 pi I n x system, but you can't take out 2. So it's better than just being complete. How good is it? Is it actually more than that? Could it be a Schauder basis? And the answer to that is no. And there are a variety of ways to see this, but one way is a property of Schauder bases. When you look at the product of a basis element times a dual basis element, look at the product of those norms. If you're a Schauder basis, those are bounded above and below. And in a lot of the systems that we like to work with, like wavelets, Gobber systems, whatever, all the frame elements have the same norm. They're usually norm 1 even. And that's the case here. All of these x times e to the 2 pi I n x functions all have the same L2 norm. So if you are a Schauder basis, that means that your dual frame elements would have to be bounded above and below in norm. But you can just take this thing and compute it, check out its norm, and it's blowing up. So this thing is kind of unusual. It's not a Schauder basis, but it has good properties. I mean, it's still minimal and complete. And a while ago, a postdoc of mine, Yang Jung Yun, we explored these types of systems and found some results. But again, I'm not going into that direction today. But why is this system interesting to me? This system is really interesting because if you look back at the original Gobber system that Dennis Gobber talked about in his original paper, it was generated by taking the Gaussian function and doing integer translations and integer modulations applied to it. So you get, now there's the index set is two-dimensional. You've got n's and k's, but you've got e to the 2 pi I n x times a translate by k of the Gaussian. And this was the original Gaussian system. And we know now that this system isn't the greatest for trying to do Gobber analysis because it's not a frame. It turns out that just like that x times e to the 2 pi I n x system, it is overcomplete by exactly one element. You can throw out one thing from that Gaussian system and it will still be complete, but it's not a Schauder basis, and you can't throw out two things from it. And so the system at top is kind of a simpler one-dimensional version of the Gobber Gaussian system. But in both of these systems, the index set, right, the integers take away one element, or for the Gobber system, it's z squared take away one element. Both of those systems have density 1. And you kind of say, well, is that a coincidence? Or is there something more going on there? And I want to explore that connection to density a little more. So first, let me remind you what density means. It's not bad if you're dealing with a nice lattice like the density of the integers. Okay, that's clearly 1. But how do you do this for completely irregular sets? And Hartmut's talk last week went into this in a little more detail, but the idea is, suppose that I have an index set. I'll call it capital lambda, and I'll do this for the Gobber systems. So it's a two-dimensional countable subset of R2. What's its density? Well, what you do is you go and you take a big square and count how many points are in it and divide by the volume. You can use a ball, you can use a square, you can use basically whatever sets that you like. But you do that, and it gives you basically the how many points per unit volume there are. So that ratio, the number of points in the square divided by the volume, kind of is the average number of points per unit area. But it makes a difference where the square is because the set is irregular. So you can move it around and get different averages. So you go and you move it around everywhere that you can and look at the two extremes, the smallest number on average, the largest number on average, and then let the square expand and look at the asymptotic limit of that. And that gives you the upper Berlin density and the lower Berlin density. In some sense, the greatest average number of points per unit area and the smallest average number of points per unit area. If you do that for a lattice, alpha z cross beta z, you get 1 over alpha beta. But think about something like half a lattice, right? In that case, on one side, when you move the square into the place where there aren't any points at all, the average is going to be 0. And then on the other side, where you do have the lattice things, the average is going to be 1 over alpha beta. And so you get a difference between the upper and lower Berlin density. And if you know things about Gobber systems, you already know how this relates to frame properties and things. Or if you just think about something like, when we do something like the classical sampling theorem, there's an aliasing component to that theorem. You have to have enough translates in the sampling theorem in order to be able to reconstruct band limited functions. And kind of the same philosophy here may suggest that you have to have enough points somehow to be complete, right? If you're going to have a Gobber system, some irregular set of time frequency translates, you think that set has to have enough points. It has to have density at least one, kind of an uncertainty principle type of criteria. That's my guess. Now let's look at some situations, okay? First off, that's false. And Dave Walnut and I gave an example way back of a system that's complete and has small density. And it's really just a modification of something that Henry Landau did, a classic result about exponentials on unions of intervals. But I'm going to give some more surprising results than that. It turns out that that conjecture is not just false, it's really false. You can have sets that only have translations, right? So they're Gobber systems, but they don't have any modulations in them. You can have a countable set of translates that's complete. And it's not something strange like taking the index set to be the rational numbers or some dense thing like that. You can do this with countable sets. The oldest example that I'm aware of, and I wouldn't be surprised if there are older examples, but there's one that goes back to Zollek in 1978. And he showed it that if you take the Gaussian and you take a particular countable set of translates of the Gaussian, you can get something that spans, that's complete in all of L2 of R. It's not like the Shannon sampling theorem, where you take translates of the sinc function and you get an orthonormal basis for the Paley-Wiener space. That's only a subspace of L2 of R. And in a sense, it's a very small subspace of L2 of R. Here, you're getting something whose span is dense in all of L2 of R and just from translates. Now, the bad thing about it is that the set that he constructed, there's more and more points per unit interval as you go off to infinity. So if you think about its Berling density, okay, as a subset of the real line, how many points per unit interval, you're getting more and more and more. The upper density is infinite. But I want to think of this not as a set of translates really, but as being a special kind of Gobber system where all the modulations are zero. So then you're thinking of this set as being indexed by translations and modulations. The index set is a subset of R2 then, but your points all lie on the translation axis, right? The modulations are always zero. And if you think about that as a Gobber system with your index set being a subset of two-dimensional space, the lower density is zero, right? Because as soon as you move your rectangle out into the place where there are no, right, off the axis where there are no points, there are no points in that square. So the lower densities is zero. And my conjecture was that you had to have density 1, right? So this is a very, very thin set of time frequency translates that's still complete. But it does have more and more points as you go out to infinity. And so the upper density is still infinite. But there's a much more surprising result.
Chris, can I ask a question about that?
Yeah, go ahead.
So this is the two-dimensional density, right? So that means that the number of points off in infinity are growing at least as fast as R squared.
That's right.
Not as fast as R, right?
Yeah. So you have to look at what the actual equation is for where the points are, and they are increasing pretty rapidly as you go out.
Just a question that, can you reduce that? Can you make that upper density finite? Is that known as this sharp? Is this a sharp result here?
No, in fact, and then that's what I am gonna change the function, and I don't know the answer if you stick with the Gaussian, but I'm going to give you an example on the next slide with a different function where the answer is yes, I can reduce this by a lot.
Oh, great, thanks.
So the next slide, to me, is a really surprising result. And this next result is due to Olevsky and Ulanovsky. I'm giving the combined result. Olevsky had a result first, and then together they improved it. But you think about how could I get a complete set of translates? It's pretty clear that you can't do that with a regular set of translates. If you just translate it by integers, for example, you could just take the Fourier transform. The translations turned into modulations, they're all one periodic. And so you get a one periodic function times the Fourier transform of your weight. And there's no way that functions like that can be dense in L2 of R. And yet, Olevsky and Ulanovsky proved that if you perturb that just ever so slightly, right, a small perturbation of the integers, you can create a complete set, right? Something that whose span is dense in L2 of R, not in a small subspace, but in all of L2 of R. And in their construction, the perturbations are actually decreasing rapidly. The farther you go out, you're very, very close to an integer. And you do this with a pretty nice function too. I believe it's a Schwartz class function that they construct that does this. So it's just an incredible construction. And if you think of this as a Gobber system, right, in R2 now, that's density zero. Again, you're in two dimensions, so you're dividing by the volume of a square, R squared, and that's right. That's going to give you the zero density if I'm doing my calculations in my head correctly. So incredible. I mean, you have almost no elements in a sense compared to a Gobber system, and yet it's complete. All right, but how nice can it be? Can these be frames? Can they be bases? I mean, I've got a complete system. How good are they? Well, there is a conjecture by Olson and Zollek, Tim Olson and Richard Zollek. 1992, they conjectured that this kind of construction, using just translates, you'll never be able to create a Schauder basis. And the precise definition of a Schauder basis, I gave it down at the bottom of the screen here. A Schauder basis is something where you have unique representations, but you have to choose an ordering ahead of time. So you fix an ordering of your index set. And with respect to that ordering, every element has to have a unique representation. So if you have a Riesz basis, the difference is that the series converge unconditionally. The ordering doesn't matter for a Riesz basis. So if you're a Schauder basis that's not a Riesz basis, then there's a certain amount of delicateness to this. You just, right, you can't just do your orderings arbitrarily. You have to have chosen an ordering. Well, in that same paper, 1992 paper, Olson and Zollek did prove that you cannot get a respaces this way. There's no way that a set of translates can be a respaces. And later in 1999, Ole Christensen and Baichao Deng and I, we proved something that gives as a corollary something about translates. We proved that my conjecture about density is true for frames. If you have a Gobber system that's a frame, you have to have enough elements, right? You have to have both translates and modulates, and the density has to be at least one, the lower density. So that means that you have things throughout the entire plane. Your index set can't just be concentrated on an axis or something like that. It's got to take up the whole, be spread through the whole plane with at least one element per unit area. So a set of translates, that's a Gobber system where the index set only lies on one axis. That can't be a frame then. Now, both frames and respaces, again, the difference there is that they have very robust representations. And in finite dimensions, there's no convergence issues like this to worry about. There is no difference between a Schauder basis and a respaces in finite dimensions. But in infinite dimensions, there are a whole range of subtleties like this. And although I've ruled out here that you can't have a frame of translates, that still leaves open the possibility that you might have something a little more delicate. And just as an example, so to give you another open question, if you look at just sets of exponentials in L2 of 0, 1, just take e to the 2 pi, some frequency x. Not necessarily regular or anything like that. Again, there are density conditions on when that will be complete or whatever. We know when you'll get a respaces. Question, is there a set of exponentials that is a Schauder basis for L2 of 0, 1, but not a respaces? That's actually an open question. Could there be some set that gives you these delicate representations, but not the robust unconditional types? That's an open question. And the Olson-Zollek conjecture likewise is open. Can you have a set of translates that's a Schauder basis? That is an open question. Deng and I were able to prove some things. A Schauder basis would have to be sparse in a sense. Density can't be too big, which again tells you, okay, respaces, well, they're both of these things. They'd have to be density 1. And we were able to prove that if there is a set of translates that's a Schauder basis, then your generator is not very nice. It's not integrable. It's an L2 function, but it's not integrable. But this conjecture is still open. It's not as famous as HRT has become, but I think it's a really interesting conjecture still. We did prove some things about Gobber systems that are Schauder bases, and I think I'll just skip that part. Olson-Zollek is open. And these things that are Schauder bases do exist, and you can characterize them as well. One example is to just take a function whose reciprocal is L2, but which is not bounded above and below, something like x to the minus 1/4 on an interval. You can use that to create a Gobber system. And it's easy to see that this is minimal. It's much more delicate to see that it actually gives you a Schauder basis, but that all comes back to that Hunt-Muckenhaupt-Whedon criteria that they characterized the weights that do give you Schauder bases in L2 of 0, 1. It's basically the same thing here. There's a condition based on, you have to have a little more than just being the reciprocal being L2. There's a kind of complementarity to the size of the weight and its reciprocal. And okay, so Alex, Paul, and I did this, taking a bit more credit than perhaps is due, because it really comes down to Hunt, Muck, and Hop Weeden things, except in 2 dimensions. And you have to create the correct ordering and so forth. But okay, let's go back to those, the system that started the whole discussion, those ones that were over complete by exactly 1 element. So take the Gaussian, take integer translates integer frequencies, delete 1 element, and you've got something that is both minimal and complete. Okay, so my guess now is, I know frames have to be dense. They have to have density at least 1. I'll bet that these exact systems, they're so close to being Schauder-based, I bet they have to have density 1 as well. And this example, right, here's the example that supports my conjecture. The original Gobber Gaussian system, 1 element removed from Z2, density 1. Okay. So then, Gerard Arsensi, Yuri Lubarsky, Christian Sipe, they came along and said, keep the Gaussian. Take these sets, this particular set of time frequency shifts. So the first index is the time shift. So you have shift in time by 1 and -1 with 0 frequencies. And then put points on the 2 axes. So you use both axes, but all the points are on the axis, one of the 2 axes. And if you take your points appropriately, you put them at square root of 2n on the axes. Then you get an exact system. And this thing, all right, the points are only on the axes. So there's, the whole quadrant has no points. The first quadrant has no points. So the density, the lower density is 0. It is true that you're getting more and more points on the axes. So the upper density is bigger. Now I'm worried about the 2-dimensional aspect that John brought up. Is it really infinite? Okay. I'm questioning myself now, but I'll leave that as an exercise for the listener, whether I did this calculation correctly. But in any case, it's a very thin set of time frequency shifts, but it still gives you an exact system. And it's kind of amazing to me that you can use the Gaussian in these 2 different ways to create a set that has a biorthogonal system. Both of these have biorthogonal systems, right? They have dual systems, but with very, very different sets of time frequency shifts. And I don't know how typical this kind of situation is. I don't know if this can be generalized or not. The proof that essentially Lubarsky and Sipe used, it depended very heavily on a relationship between the Gaussian and a particular analytic function. That set of points that they use is the 0 set of a particular analytic function. And so I don't know whether that generalizes, whether it gives you any insight into exact systems in general. And I don't know if you can create a set of translations, for example, just pure translations that is exact. I don't know if you can do that or not. But I would like to point out something with translations that's surprising. You know the translations are linearly independent in L2. It's easy. You just take the Fourier transform of any finite linear combination. If you have a finite linear combination that's 0, Fourier transform it, you get a trigonometric polynomial times g hat. The trigonometric polynomial has only countably many zeros. G hat is 0. And if p is less than 2, you can do exactly the same thing. What happens if p is bigger than 2? And you try to do this very simple argument. G hat, when p is bigger than 2, g hat is a distribution. And you can have distributions like g hat could be delta. And then just because the product is 0, that doesn't tell you that g hat is 0. You can have distributions that are supported on sets that have 0 measure. So the argument doesn't go through when p is bigger than 2. And yet, come on. There's no way translates can be dependent, right? I mean, if you go all the way up to L infinity, okay, periodic functions have dependent translates. But that's right. Okay, L infinity, so what? Functions just can't have dependent translates. I don't believe it. Well, okay, so there's a argument here, but an amazing result due to Edgar and Rosenblatt, 1979. Let's just look at the corollary. Yes, translates are linearly independent for all p's up to a point. Now, if you're in one dimension, this limit here, this 2n over n minus 1, well, that's infinity. So yes, indeed, translates are independent in LP for all p finite. But if you go to 2 dimensions, this becomes what? This is 2 times 2 divided by 1, which is 4. If I'm, it's a risk trying to do arithmetic while you're giving a talk, but I believe that's 4. We know then that translates are linearly independent up to 4. And they proved that this is sharp. Past 4 in 2 dimensions, there are functions that have dependent translates. I don't know, it's just, it's a big surprise to me, right? In 2 dimensions, just in L5, there's some function in L5 that has linearly dependent translates. So that's just, I don't know, that's just incredible. And of course, that's a segue into finite linear independence, which brings me, of course, to the HRT conjecture, which if you don't know it, this is what it says. It says that time frequency translates in L2 are just like translates in L2. They're independent, linearly independent. You can't get a finite linear combination that's 0 except for the trivial one. Right? If you take an L2 function, you take finitely many points, the sum of ck either 2 pi I bkx times g of x minus ak, if that's 0, then all the coefficients have to be 0. That's still, almost 25 years later now, that's still open. And in fact, here's the current smallest, or one of the smallest subversions of this that's still open. Take just 4 translates. Is HR2 true when you only do 4? We know it's true with only 3 translates. Is it true with 4 translates? And that's still open. And here's a very, very specific case. G of x minus 1, g of x e to the 2 pi ix And then the last one that has both a translation and a modulation. G of x minus square root of 2, e to the 2 pi I square root of 3x. Are those linearly independent? Are those four functions linearly independent? And that's open. Even if you put very strong conditions on G, even if you restrict to Schwartz class G, this is an open question. Now, over the years, I've had to change my subconjecture a little bit. The current version, the previous version had root 2 and root 2. I've now had to change that to root 2, root 3, because I believe that Caso has settled the root 2 result. But there's something amazing number theory at work here. Root 2, root 3 is still open. Well, I promised in my abstract that I would tell you something new about the word frame. So let's go back just to end the talk. Duffin and Schaeffer introduced frames. And unfortunately, we didn't ask them why they called them frames. And in fact, a few years ago, I had an article in the notices of the AMS about what is a frame. And I said this explicitly. We never asked them, why is it a frame? One guess is that, well, right, the sum here is kind of framed between the upper and lower bounds. And we didn't think to ask them. And so I said, we will never know. But there is more to the story. After I published that, a colleague of mine, Tom Morley, in my department, he's retired now, but he was a student of Duffin. And after seeing my article, he came to me and he told me that he had talked to Duffin about frames. It's something they had discussed when he was a grad student. And according to Tom, they use the word frame because it's a kind of generalization of a basis which gives you a frame of reference. So I have it on fairly good authority that that's what frame means. You've chosen a frame of reference. Now, I can't swear that that's actually true, but it comes from Tom, who was a student of Dick Duffin. So that's the little teaser that I threw out in the abstract. Thank you very much.
All right. Thanks so much. I'm going to hit this reaction button here. I encourage you all to do the same. And if Dustin could, or Emily, if you could stop the recording.